In this lecture, let us understand about the superconductivity. In the previous lecture, superconductivity was not discussed, but the electrical conductivity in the normal conductors was discussed. And it was told that the electrical conductivity is temperature dependent in all types of materials. In a conductor, the electrical conductivity increases with decreasing temperature, or electrical resistivity decreases with decreasing temperature. It was discussed. However, although there is decrease in electrical resistivity with the decreasing temperature, it does not reach zero even when the metal is cooled down to 0 degree Kelvin. The reason was explained. The graph that was shown was this in the last class. Here it was told that when the temperature of the metal is decreased down to a low temperature, even up to 0 degree Kelvin, the resistivity decreases but not to 0. It was told that in a conductor, the scattering of electrons takes place not only by the thermally agitated ions but also by the impurity atoms present in it. The impurity scattering is almost temperature independent. But when we decrease the temperature, the thermal agitation decreases, so which causes the resistivity to decrease. That is the phenomenon that happens in a conductor. Whereas in a superconductor, when we decrease the temperature, there also the resistivity decreases, but at a specific value of temperature, there will be an abrupt fall in resistivity to 0. It can be graphically shown with this diagram. It can be observed that when the temperature is decreased, the resistivity also decreases. When the superconducting material is cooled down to a temperature, at a specific temperature called critical temperature, the resistivity comes down to 0. The reason for this abrupt fall in the resistivity can be understood from the BCS theory, which will be discussed in my next lecture. The resistivity fall to 0 was first observed by a scientist called Kamerlingh once in 1911, when he was cooling a column of mercury in the capillary tube which was immersed in the liquid helium. Its resistivity came to 0 at a temperature about 4.2 degree Kelvin. This opened up a new class of materials which were known as superconductors, a phenomenon in which a material shows 0 resistivity at or below a critical temperature is known as superconductivity. Any material that has the ability to possess 0 resistivity is known as a superconductor. The electric current that persists for a very long time in such a superconductor because of no resistivity, hence it is called supercurrent. In this lecture, we are going to understand a few properties of the superconductors. For example, Meissner effect. Meissner effect is a phenomenon of expelling the magnetic lines of force by a superconductor. It shows the diamagnetic property. I will explain with an example of an experiment. I will demonstrate how the magnetic lines of force are expelled by a superconductor. So the Meissner effect is the phenomenon of expelling the magnetic lines of force. When a magnetic field is applied to the superconductor, it doesn't allow the magnetic lines to pass through it. The magnetic flux through the material is said to be 0. This is the Meissner effect. We will understand it diagrammatically how this happens. In addition to this, we will understand the type 1 and type 2 superconductors what are their properties, which one is preferable for applications. So these are the topics to be covered in this particular lecture. Demonstrate the Meissner effect phenomenon with a simple experiment in which assume that this is a superconducting material and one primary coil is wound round it, connected to a cell or a battery, and assume that there is one more coil, secondary coil. We can say it is the secondary coil, this is connected to a galvanometer. In this simple experiment, superconductor or superconducting material at normal temperature. Now it is not maintained at the temperature below critical temperature. Critical temperature is already defined. It is the temperature at which the normal conductor becomes superconductor when it is cooled from a higher temperature. Now assume that this superconducting material is at room temperature. When this key is closed, there will be the rise in the current in the circuit. Some current is raised. Due to the rise in the current from 0 to, let us say, 1 ampere. When the current rises from 0 to 1 ampere after the switch is closed, we say that there is change in current. This change in current induces a magnetic field that is also changing. When there is change in the magnetic flux linked with the secondary coil, there will be a current induced in it. We have learnt the mutual induction in our previous courses. So, due to the mutual induction phenomenon, when a current is made to change in primary coil, an EMF or the current will be induced in the secondary coil, which leads to the deflection in the galvanometer. A non-zero deflection can be observed in the galvanometer. But after some time, the current becomes constant because we have connected a DC power supply. It's a cell or a battery. So that current becomes steady. When the current becomes constant, there will be no induction of EMF in the secondary coil. Therefore, this galvanometer deflection comes back to zero. Now, let us cool down the superconducting material from room temperature down to a lower temperature. If we cool this superconductor down to the lower temperature, that temperature should be below Tc. You have to cool the superconducting material to a temperature below Tc. When it is cooled down to this temperature, it can be observed that there will be a sudden deflection in the galvanometer. Now let us understand why this galvanometer deflects when the superconductor is cooled below the critical temperature. In fact, when it is cooled below the critical temperature, the superconducting material develops the surface screening currents which will induce a magnetic field or magnetic flux within it. Let us say Bi is the magnetic flux developed internally. So when that magnetic flux is developed, that will induce an EMF again in this secondary coil, which leads to the deflection in the galvanometer. So the surface screening currents formed within the superconductor develop a magnetic field within it, which in fact opposes the external magnetic flux. So if you say Bi is the magnetic flux developed due to the surface screening currents, and B as the magnetic flux which was externally linked to the material, they are opposing each other. When they become equal in magnitude, the effective magnetic flux within the material is said to be zero, similar to this diagram. Here the superconducting material appears as expelling the magnetic lines of force, whereas at the temperature greater than Tc, the magnetic lines of force can be penetrating through the material. This is at the temperature higher than critical temperature, and this is the case when the temperature below the critical temperature. It is clear that the superconducting material is diamagnetic at the temperature below the critical temperature. Now, at the temperature below critical temperature, if we apply the magnetic field to the superconductor, assume that this is the superconductor. If a magnetic field is applied, let us say H, if the magnetic field is applied, then the superconductivity can be modified. It can be affected by the external magnetic field. If we go on applying the magnetic field, if we go on raising the value of the external magnetic field starting from 0 at a particular value of H, let us say Hc, the superconductor turns back to conducting state. Superconductor becomes a normal conductor. That is the critical magnetic field. So critical magnetic field is the minimum magnetic field required for turning the superconductor to the normal conductor. And this critical magnetic field is not the same at all temperatures. It is temperature dependent quantity. The critical temperature is very small, critical magnetic field is very small at the temperature equal to the critical temperature, whereas it is maximum at 0 degree Kelvin. It can be shown diagrammatically that the critical magnetic field varies with the temperature, and it is the highest at temperature equal to 0 degree Kelvin, and it decreases to 0 at the temperature equal to Tc. And there is a relation to show this critical temperature. Hc equal to h naught into 1 minus T square divided by Tc square. This h naught is the highest value or maximum value of Hc, that is at T equal to, this is Hc value itself at temperature equal to Tc. So that maximum value of the critical magnetic field. So this diagram shows that the critical magnetic field is not the same for all temperatures. And we also understand that if the superconductor is maintained at a very low temperature, let us say it is 32 degree Kelvin, critical temperature is 32 degree Kelvin. If the superconductor is maintained at a temperature about 1 Kelvin or 2 Kelvin, if it is very small compared to 32 degree Kelvin, then the critical magnetic field required to turn the superconductor to normal conductor is very high. Let us say, for example, 2 Tesla. It may require 2 Tesla of magnetic field. So when the superconductor is subjected to such a high magnetic field, then even at such a low temperature, it is very far from the critical temperature. So even at this lowest temperature, it is possible for the superconductor to lose its superconductivity. So if the temperature is maintained at, for example, 10 degree Kelvin, then the critical magnetic field required need not be 2 Tesla. It may be 1.5 Tesla at 10 degree Kelvin. Similarly, if the material is maintained at 20 degree Kelvin, the magnetic field required is just 1 Tesla. So this is how the critical magnetic field depends on material. And when the temperature approaches critical temperature, naturally the material itself turns to normal conductor. It does not require the magnetic field to change it. Therefore, we say that at T equal to Tc, the critical magnetic field value is 0. Because above the temperature, that is above the critical temperature, material does not have superconductivity. So there is no question of requirement of the critical magnetic field to turn it to the normal conducting state. So this is the diagram showing superconducting state at the temperature below Tc. This is the normal conducting state. Now let us look into the types of superconductors. Superconductors are classified as type 1 and type 2 superconductors based on the number of critical magnetic fields exist. Type 1 superconductor has only one critical magnetic field, whereas the type 2 superconductor will have two critical magnetic fields, which I will explain later. And both the superconductors exhibit the Meissner effect, but the type 1 superconductor exhibits complete Meissner effect. That means when the magnetic field approaches the value of Hc, the material turns completely into normal conducting state. So here I am showing the graphical representation of negative magnetic moment against the applied magnetic field. It is the negative magnetic moment because the superconductor is diamagnetic in the superconducting state, that is at temperature below Tc. So at this temperature, since it is diamagnetic, then magnetic moment is shown to be minus m. And if we increase the magnetic field, then there will be the increase in the negative moment within the superconducting material. But when the magnetic field approaches the critical value, there will be an abrupt fall in the value of the negative magnetic moment. For all values below Hc, that is for H less than Hc, there will be no flux penetration. Flux will not penetrate through the superconducting material because it was showing the Meissner effect. There was absolutely zero magnetic flux through the superconducting material at H less than Hc, hence it is called complete Meissner effect. But beyond the value of the magnetic field Hc, there will be normal conducting state. The material shows normal conducting state even at the temperature well below Tc. This is what explained. The magnetic moment variation with H takes place at a given temperature. And in the case of type 2 superconductors, the variation is little different. Let us say it is minus m and this is H, magnetic field, applied magnetic field. In this case, when we start rising the magnetic field at a given temperature, that is at T less than Tc, if we raise the magnetic field applied, the negative moment also rises, but on reaching a specific value of Hc1, the magnetic moment start decreasing but does not come down to zero abruptly as happened in the case of type 1 superconductor. Instead, it will decrease in an exponential form. It decreases this way. And at the value, at any value below Hc1, H less than Hc1, there will be absolutely no flux penetration. Complete Meissner effect is possible here. But another value of the critical magnetic field is Hc2, where the magnetic moment becomes completely zero. Between Hc1 and Hc2, flux penetration is partial. There is no complete vanish of the flux penetration, but partial flux penetration takes place within the material. So this is the major difference between the type 1 and type 2 superconductors. In the case of type 1 superconductor, Hc value is very small. It is of the order of just 0.1 Tesla. Such a superconductor cannot be used to make the superconducting magnets, because if, for example, Hc value is 0.1 Tesla for a given superconducting material, and if you are using that superconducting material to produce the magnetic field, when the magnetic field produced becomes equal to 0.1 Tesla, immediately the material turns back to the normal conducting state. Therefore, the maximum magnetic field that can be produced using a type 1 superconductor can be anything smaller than 0.1 Tesla. So this is not preferable for superconducting magnets. That is the reason why type 2 superconductors were developed. 2 superconductor, although Hc1 is very small, it may be 0.1 Tesla or 0.2 Tesla, Hc2, nowadays Hc2 has approached even up to 10 to 12 Tesla. Therefore, type 2 superconductors can be used to produce the magnetic fields even up to 10 to 12 Tesla. The state between this Hc1 and Hc2 is known as vortex state, and in this state also the superconducting material offers zero resistivity. That means starting from 0 Tesla to Hc2 value, the material shows zero resistivity. Although there is partial flux penetration, zero resistivity is possible. That means the material behaves purely as a superconductor up to Hc2. Let us understand the reason. In a type 2 superconductor, especially in the vortex state, there will be cylindrical swirl of supercurrents. I can show it diagrammatically here. Assume that this is the superconducting material. These are the magnetic lines of force penetrating through the material. This is actually, this space can be treated as the superconducting state, whereas this portion acts as the normal conducting state, that is within the vortex state. So in the vortex state there will be some swirling currents, swirling supercurrents through which the flux penetrates. So this is the region where there are the supercurrents swirling, and within these currents the magnetic flux penetration can take place. That is the reason why there will be the decrease in magnetic moment, but not abruptly to zero, but slowly. If we go on increasing the magnetic field, such regions of swirling supercurrents will increase and the superconducting regions will decrease. Therefore, there will be the decrease of magnetic moment, and when the value of the magnetic field reaches Hc2, such the magnetic line penetration takes place everywhere throughout the material. Therefore, the material turns back to the normal conducting state at temperature at magnetic field equal to Hc2. The advantage of type 2 is already mentioned, that it is advantageous for producing the superconducting magnets. The efforts are on to produce this type of superconductors because of many application requirements. It is found that copper oxide superconductors have Hc2 even close to 15 Tesla. Therefore, the copper oxide superconductors can be used for the superconducting magnets to produce the magnetic field even up to 15 Tesla.